to the third lecture in Module 4 on solution of discrete algebraic systems. We had already seen the features of discrete algebraic systems, solution methods for nonlinear systems, and direct and basic iterative methods for linear systems in previous lectures. Today, we shall focus on accelerated iterative methods for linear systems. So, let us have a recapitulation of what we did in lecture 2 of this module. We discussed direct solvers for discrete linear systems specifically suited for CFD applications. In fact, we had a detailed look at what we call tri-diagonal matrix algorithm or TDMA, which can be used for one-dimensional problems, and it can also work as a backbone of an iterative scheme based on alternative direction method. Then we started off with iterative methods for linear systems, which are the most commonly used in CFD programming, and we discussed some basic iterative methods which are generally very slow to converge, but nevertheless they are very important for accelerated methods, and that is what we are going to focus today at accelerated iterative methods for linear systems. So, outline, we will look at the category of methods what is known as projection method, and then we will look up a specific type of projection method which we call Krylov subspace methods, and we will look at the preconditioners which are required in these methods, their basic characteristics, and then we will have a look at one method in detail for symmetric systems. Then we will enumerate the methods for general systems which are not symmetric, and in the end we will have a look at a very popular and very powerful class of methods which is called multigrid methods. Now, what is a projection method? It is again an iterative scheme, and here we will introduce some terms from the vector algebra, that given an available iterate x, let us say x naught, we have to find a new approximant x which will basically be from a set of vectors x0 plus k such that this residual b minus ax is orthogonal to a tensor subspace which is shown as lambda here. Now, here k is called the search space or search subspace, that is to say we are going to take out some vectors from this subspace to get our new iterate, and your lambda denotes the subspace of constraints. For a detailed and more definitive definition of projection methods, please have a look at the book by Saad published in 2003. We will give the complete bibliographic detail of this book towards the end of the lecture. Now, this Krylov subspace method, they are a specific type of projection method wherein the subspace k, that is our search subspace, is Krylov subspace k subscript m defined by km a comma r naught. R naught is a residual vector, it is a span of these vectors r0, ar0, a square r0s and so on up to a to the power m minus 1 r0, where a is our system matrix, and in approximate solution xm is of the form, xm is our new iterate, so xm is x0 plus qm minus 1 a r0, where qm minus 1 is a polynomial of degree m minus 1. So, this is the formal representation of the new iterate. Of course, we will not actually compute any of these polynomials in real practice in real algorithms, that is just the starting point. Now, in Krylov subspace methods we can have different type depending on the subspace of constraints chosen. So, different choices of subspace of constraint leads to different Krylov subspace methods. For instance, if our lambda m is same as km, that is our constraint space subspace is same as the search subspace, then we get what we call conjugate gradient method for symmetric linear systems. And in case if we have lambda m is equal to a km, we get a powerful method called gmpress for general linear systems. So, there would be different possibilities for different types of Krylov subspace methods. For details, please refer the book of Saad indicated earlier. Now, performance of a Krylov subspace solver such as our conjugate gradient or GMRS depends on two factors. The first factor is the choice of preconditioner which we use in these methods, and the preconditioner primarily affects the convergence of iteration, and it also affects the overall computing time, because if each call to preconditioner is very time consuming, that is going to affect our overall computing time as well. Similarly, if the number of iterations are large, then again our computing time would be affected. So ideally we would like to have a preconditioner which takes less time per iteration step and it converges very fast. So another factor which will affect the performance is the time, or rather number of operations which are required to compute matrix vector products. So in fact this is the most time consuming sequence of operations involved in Krylov subspace methods, whether be it PCG or GMRS. So the time taken by this matrix vector products, it affects the overall computational efficiency of a Krylov subspace algorithm, and we can easily see that our matrix sparsity pattern would affect the computational operations required in obtaining our matrix vector product. So this particular thing is dependent on the sparsity pattern of the matrix. Fortunately, in CFD applications we will have very sparse matrices, so matrix vector products can be obtained very efficiently, and this is one of the reasons why these Krylov subspace solvers are very popular in CFD for large scale problems. Now let us have a look at some properties of preconditioners. So preconditioners are required to ensure that our method is a robust and efficient solution algorithm. So what are essential properties of a preconditioner? If you look in bit more detail, which we did not have time today, the iterative solution process, the convergence is linked to the eigenvalues of our matrix. So a preconditioner should help cluster the eigenvalues of the preconditioned system, which is obtained after pre-multiplying the preconditioner to a system matrix. So if they are clustered together, that ensures faster convergence. And the next one is a very important restriction which we have got. The majority of Krylov's subspace solvers, they require that a preconditioner must be a constant linear operator in all the iterations. We cannot have a variable operator or a non-linear operator as our preconditioner for Krylov subspace methods. Now there are some desirable properties, desirable in the sense that they may not hold good for all choices. So a preconditioner should take as little time as possible, that is what we would desire, and the second is it should result in a small number of iterations, and the number of iterations should be independent of the problem size. Now both of these are conflicting requirements. If we have a preconditioner which takes a very little time, for instance if we use Jacobi's method or Gauss-Seidel method as a preconditioner, those methods are very fast, but the number of iterations required would be much larger with Jacobi as our preconditioner. And if we use a better preconditioner, like for instance we use Multigrid as a preconditioner, the computation time taken by the preconditioner would be fairly large, but we would get a very small number of iterations for convergence, and further we would see in one or two numerical examples today that Multigrid used as a preconditioner results in the required number of iterations which are independent of the system size, whether the system size in thousands or millions or billions. So that is why we say there is a trade off between the preceding two desirable properties. We choose a preconditioner which requires less time, the number of iterations would be increased and so on. So we ultimately the overall computing time might suffer with such schemes. Theoretically, for faster convergence, the preconditioning matrix or operator, as the case may be, must be a close approximation to matrix A, where A is our system matrix. Why I have mentioned the word operator here is that we might also use certain sequence of operations and their effect would be what we call the effect of preconditioner. For instance, multigrid process itself cannot be represented as a matrix, but it is nevertheless a form of a linear operator and hence can be used as a preconditioner with a Krylov subspace solver. So in all our discussions on Krylov subspace methods, wherever we see the algorithms, we would put a symbolic form, symbolic term M inverse, which would M inverse multiplied by a residual vector, that would give us the effect of the preconditioner. But M inverse is not M is not a matrix per se, it is just M inverse multiplied by the residual, that is the effect which we are looking for with our preconditioning operator. So what are the most commonly used preconditioners? The simplest one to use is Jacobi or diagonal preconditioner, but please remember this is a very fast preconditioner, but the number of iterations required are pretty large. In fact, theoretically the convergence of a Krylov subspace method would be ensured in number of iterations proportional to the system size. So this is not an ideal situation. So Jacobi preconditioner results in very fast, it is very fast per iteration step, but results in poor rate of convergence. So our overall computing time might still be pretty large with Jacobi preconditioner. Then recently incomplete LU factorizations have been developed. LU factorization results in a large number of fill-ins. So where do we cut off those fill-ins? That would decide the effectiveness of these preconditioners. So the word incomplete we use because we won't carry out the LU decomposition process in full. It will be stopped when certain allowed number of fill-ins are reached. This region is called ILU or incomplete LU factorization preconditioner. There are a variety of them available in literature which you can look into the standard books which I have just cited. These are very effective, but there is a problem with fill-ins. What do you mean by fill-ins? Our system matrix is very sparse, but the operate matrix which we get, preconditioning matrix which we get from incomplete LU factorizations might not be as sparse as our original system matrix. So there might be memory trade-offs required with incomplete LU factorizations, and the matrix products, matrix vector products which we require with preconditioner, that would also be pretty expensive. The next subcategory of preconditioners what we call approximate inverse preconditioners. What we said that look, if our preconditioning matrix A is close to our matrix system matrix A, then that would result in a very fast convergence rate. So that is what this approximate inverse preconditioners aim at. And there are a few categories here, like block diagonal preconditioners is one of them, and we can also obtain approximate inverse preconditioners based on what we call Frobenius norm minimization. For details of these ILU or block diagonal or Frobenius norm based what we call sparse approximate inverse preconditioners, please have a look at the book by Sarr. And in the end I would like to just mention this popular very powerful preconditioner, multigrid preconditioners. Later on we would see that multigrid algorithm can be used as a very efficient stand-alone solver, but there are certain situations wherein instead of a solver we can use multigrid as a preconditioner to a Krylov subspace algorithm, and the use of multigrid with the Krylov subspace algorithm results in what we call an optimal method, for which the number of iterations required is independent of the system size. Now next we will have a look at a Krylov subspace solver for symmetric systems. In fact, we would put some more requirements here. We are looking for symmetric as well as positive definite linear systems. So there are quite a few Krylov subspace methods available for this family, but the simplest and most commonly used Krylov subspace method is preconditioned conjugate gradient method, or in short we use this term or acronym PCG. We will have a look at the details of this algorithm. It is very elegant and very simple to program, be it for a serial machine or a massively parallel distributed memory machine. So that is the reason if we are sure that our system matrix is symmetric and positive definite, which is very often the case with the solution of Poisson's problem on central difference grids and finite element grids. So in such situations PCG can be used for solution of a Poisson problem. Now in the algorithm which we are going to have a look in detail is the preconditioning step would be represented by Z is equal to M inverse R. Okay. But we will not attempt to even just form M or forget about taking inverse of M. All that we mean by this particular step is solve a system of this type mz is equal to R, this particular linear system, solve it and get a vector z which is used in this algorithm. And M may not even be explicitly defined, we only need an operator which is constant in each iteration, and that operator is represented by the symbol M. So now let us have a detailed look at our PCG algorithm. So preconditioned conjugate gradient method. Since it is an iterative procedure, so we would require that we start off with an initial guess, and we would like our iteration to terminate somewhere. So when we should terminate the iterations, we should also have to specify some tolerance for the convergence of our iterations. So that is the first step which we need to fix in, that we have to set our tolerance for convergence, set a tolerance for convergence check, and choose an initial guess let us represent our initial guess by vector x naught for solution of system of equations, which we are going to represent as a x is equal to b. So now let us write it in a pseudo code form or algorithmic form. So suppose we begin our subroutine, begin PCG. What we need to first do is, given our initial guess x0, let us compute what would be the initial residual. So compute residual. What do we mean by residual here? Substitute this initial guess x0 in our system. Okay, that will not satisfy it. So let us find it for the differences. So residual R0 would be defined as our vector b minus matrix A times our initial guess x0. We will also do some more computations. So this is one computation, compute residual R0, then Next computation which we would require is to invoke our preconditioner. So, find out or solve this system to get our initial guess for the vector z, which we call z0. So, M inverse R0, and we would introduce few vectors here. So, we will introduce a vector P0 is equal to Z0. So, these are few things which we will do before our iterations start, that is compute the residual vector, solve a system of equations with our preconditioner. So, M inverse R0, basically this represents our effect of preconditioner, and then we will introduce a vector which we call P0, which is related to search directions. P0 is equal to Z0, that is what we are going to initialize. Now, next we will now start our iteration process. So, let us see for j is equal to 1, 2 and so on until convergence. We have to repeat certain set of statements. Okay, so, now let us write down those set of statements which are to be done at each iteration. We will compute few scalar quantities which are required in our algorithm. The first scalar quantity which we are going to compute is alpha j, which is given by Rj comma Zj divided by A Pj comma Pj. Now, this bracketed term has got a very specific meaning. Let us write down in some corner. So, what we denote by this bracketed term is, this is what we call inner product or dot product of two vectors. So, this is terminology or the symbol which we have, shorthand notation which we have used to represent the dot product. So, we have computed our one scalar quantity alpha j, and once we know alpha j, we have already got a guessed or computed value for Pj, we can get the new iterate in terms of alpha j. So, new iterate xj, that would be given as, or rather let us call it xj plus 1. So, it will be xj plus alpha j times the vector Pj which we have calculated earlier. So, alpha j essentially represents a sort of a weight factor, and Pj are what we call the correction vectors. So, correction vectors multiplied by this scalar weight alpha j are to be added together to get an improved guess xj plus 1. Next, we will compute our residual, or rather for computing the residual we do not have to substitute in the system of equations, that we do not have to compute r minus a times something. We get fairly simple formula here. So, r j plus 1. So, this would be the residual for the next step. This can be obtained by, we have got the current residual, and from this subtract the vector at a Pj, this vector we have obtained earlier, multiplied by alpha j, subtracted from Rj, and we get an estimate for the residual vector. Now the norm of this residual vector can help us ascertain the convergence process. So there are various ways in which we can implement our convergence check. We can look at the norm of Rj, or the relative norm of Rj, that you take the magnitude of Rj plus 1 divided by magnitude of R0, which we started off with. So that will give us the relative convergence thing, compare it with our tolerance. If satisfied, we can say now our solution has converged. The next thing what we will do is, we are now going to compute a new set of vectors Zj. So Z of Zj plus 1, now this Zj plus 1 would be used in our next iteration to compute this alpha j and so on. So Zj plus 1 has to be obtained by solving our preconditioning system. So we would represent it symbolically as M inverse R j plus 1. Okay. So this is the effect of the preconditioner. Okay. Now we would compute yet another scalar quantity beta j. Beta j is given by the inner product of R j plus 1 Z j plus 1. So dot product of these two vectors divided by R j Z j. Now in this evaluation we would compute only one of these inner products, and we do not have to repeatedly compute in the same iteration step. We do not have to compute Rj plus 1 comma Zj plus 1 and Rj Zj. Rj Zj would be available from the previous iteration, it has already been computed earlier. So we can save it and use it here, and we can now get an estimate of the correction vector Pj plus 1. This would be given as Z of j plus 1 times beta j Pj. So the correction vector which we need to use for the next iteration, this Pj plus 1, that is obtained in terms of the correction vector which we get from the preconditioning step plus our scalar weight factor beta j into the correction vector from the previous iteration. So now this completes our one iteration, and in fact here, before we go and compute this Zj plus 1, we would also perform our convergence check. So if you want, you can do convergence check here, or you can do convergence check after computing Pj plus 1 to decide when we need to exit this iteration loop. So you can see some few nice things here, that at each step of iteration, that is to say in each iteration, we require only one call to the preconditioner, and we also require only two new sets of inner products. So programming this PCG is very easy. You can write, it's almost trivial. If you have got all that we need is, we need a routine for computing this matrix vector product, we need one routine to form the scalar or inner product. Okay. So this whole algorithm can be coded into few lines of code in any language, in C or Fortran, whichever is the language of your choice. Yes. So this PCG works very well, as we have seen earlier. This is useful, or in fact it is applicable for symmetric and positive definite systems. But in practice it also works for the systems for which we are not sure the system matrix is symmetric, but we are not very sure about the positive definiteness. Many times this algorithm works pretty effectively. So whenever our system matrix is symmetric amongst Krylov subspace method, our choice is very clear. This no algorithm which can beat PCG in terms of its efficiency. The overall computational efficiency of PCG would of course depend on our preconditioning step. So if you want to have a robust and efficient PCG algorithm to solve a system of equations, we have to choose a suitable preconditioner. And you would be surprised to know that there are lots and lots of preconditioners available in literature, and still considerable amount of research work is going on in developing newer set of preconditioners which can give us more robust and efficient version of PCG. Now let us have a look at the list of Krylov subspace solvers for general systems. So I have just listed the most popular Krylov subspace methods. At the top of the list of the priority is what we call generalized minimum residual or GMRES method developed by SAD. So this method is a bit difficult to program, but it is very efficient method for general linear systems. Then similar to conjugate gradient, we can have what we call a biconjugate gradient method for our asymmetric or general linear systems. So in this case we require two set of directions, that is the reason why we have got biconjugate gradient method, and it would require at each iteration step two calls to preconditioner, one for our normal system and one for a transpose system. So there are few methods available in the literature which do not require the use of the transpose matrices. So conjugate gradient square method is one of them, and then we have got another version of biconjugate gradient method which is called biconjugate gradient stabilized or bi-CG stab method. This is again a very robust method, and this method does not require forming the transpose of a matrix. So it can also be used for non-linear problems wherein we have formed our Jacobian matrix by taking finite differences, and finding the transpose is a very difficult task. So for these general systems, the most effective choices are what we call GMRES. With GMRES only drawback is the writing the code is a bit involved. Bi-CG step is relatively simple, it is slightly more complicated than our PCG algorithm which you have seen. Now please remember PCG and GMRES, biconjugate gradient, CGS or this bi-CG step, all these algorithms require a preconditioner which must be the same at each iteration. So take care of this problem. SAD developed one method which is called flexible GMRES method. Now this flexible GMRES, it is a variant of GMRES which does not put this restriction of constantness of the preconditioner at each step. So a preconditioner can vary from one iteration to another. So much so that we can have a flexible GMRES method in which GMRES itself can be used as a preconditioner, and thereby we get a flexible method which is pretty efficient. Now I would not go into detail of any of these algorithms. I would refer you to the book of SAD, which gives you detailed descriptions of the methods along with the algorithm and pseudocode which can be easily programmed. And now we move on to the next category of accelerated methods, which we call multigrid methods. These methods are also referred to as multi-level methods. Why they are called multi-level, it would become pretty clear very soon. So these multigrid techniques, they exploit discretizations with different mesh sizes. In normal finite difference and finite volume or finite element formulation, we will initially have one grid using which we obtain a discrete system of equations. But solving our system just on one fine grid, we can be better off if we can construct a sequence of coarser grids and use the solutions on those grids to obtain a better rate of convergence. In some cases, it may not be possible for us to form or to come up with a sequence of nested coarse grids. So in that case, we can instead form what we call coarse grid operators algebraically. So that's it. That's the reason why I have put here with different mesh sizes or operators. Here by operators I mean this coarse grid operators, and these, when applied to a given problem, obtain optimal convergence based on relaxation techniques. Our relaxation techniques here are basically our simple iterative schemes or basic iterative schemes which we have seen earlier, our Jacobi or Gauss-Seidel methods. Those are referred to as relaxation techniques in the context of multigrid methods. And how does this method work? What is the basis of the multigrid? If we analyze the errors in our convergence process, we can break down the errors in two ways. On a given grid, the errors can be classified as high frequency errors which are linked to the fine grid size, and the low frequency errors. Now if we use a relaxation technique like Jacobi iteration or Gauss-Seidel iteration, in very few iterations of Jacobi or Gauss-Seidel we can reduce or eliminate high frequency errors, but removing low frequency errors is very difficult. But those low frequency, this frequency of the errors is linked to our grid size. If you move on to a coarser grid, this low frequency error would become high frequency errors on a coarser grid, and on these grids these can be easily removed using a relaxation or smoothing scheme. We would use this term relaxation or smoothing interchangeably, okay, and the typical methods which we are going to use for relaxation or smoothing are Jacobi or Gauss-Seidel iterations. So that's the reason why if we can combine a sequence of grids, we have got our finest grid on which we would ultimately like to obtain our solution. Choose a coarser grid. On that coarser grid we can eliminate the low frequency errors, obtain a correction, add it to the solution on our finer grid, and thereby we would have an iterative technique which converges very fast. So these multigrid methods, they exhibit a convergence rate that is independent of the number of unknowns in the discretized system. We will see it numerically. We will have a look at one or two examples where we have used multigrid as a preconditioner. Okay. So in this particular sense, this multigrid methods are referred to as an optimal method, and a complexity analysis says that they are almost of order n, that is computational complexity of the method multigrid methods scales linearly with the system size. So that's it and the beautiful characteristic of multigrid methods. Now what are main components of multigrid algorithm? We are dealing with different set of grids, whether actual physical grids or a set of algebraic operators. So we need an operator R, which we call restriction operator, which maps or restricts residuals on a finer grid to the coarser grid. So we are restricting from a large number of grid points to a smaller number of grid points. That's why the word used here as restrict, and the name of this operator as restriction operator. We normally use symbol capital R for the restriction operators. So what we will do, we will use this operator to restrict our residual on a finer grid to a coarser grid, and we will solve for a correction term on the coarser grid. Once that has been solved, we now need to extend or interpolate that solution to our finer grid to obtain the solution or improved iterate. So we need what we call prolongation operator, which we will denote by symbol capital P, which extends or interpolates solution on a coarser grid to a finer grid. And then we talked about a relaxation scheme or smoothing procedure. So let us say we will symbolically denote it by the term smooth within parentheses, where we will provide it with certain set of arguments. Now these prolongation and restriction operators P and R, they will depend on the underlying differential equation, that we will have a different set of prolongation operator for, let us say, our Poisson equation and a different one for advection diffusion equation. So this prolongation and restriction operators, they will depend on our partial differential equation, and they will also depend on the multigrid strategy which we have chosen. By multigrid strategy, we will discuss next what we have got. We can classify our strategy as two types. So first one is what we call geometric multigrid, and very often in literature you will come across the acronym GMG, all capitals. So geometric multigrid is based on a sequence of nested grids. The reason we have used the word geometric is that geometrically we will actually obtain a sequence of physical grids using a grid generator, and those set of nested grids would be used in our solution process. Many times, specifically on unstructured grids, it may be very difficult to generate a sequence of nested grids. Even if you can generate a sequence of fine, coarse and coarser grids, calculation of our restriction and prolongation operators could be very complicated. So an alternative which has been developed recently in past 2 decades is what is referred to as algebraic multigrid. Now in algebraic multigrid, we actually do not form a sequence of nested grids, only one grid is good enough, that is our finest grid, and multigrid components, that is your prolongation and restriction operators, they are generated based on a purely algebraic procedure. So since we are using a purely algebraic procedure, there are many types of procedures which have been suggested in literature, the agglomeration based or Galericon procedure based. So since everything is being done by looking at the coefficients of the matrix which has been generated on the fine grid, this set of multigrid methods are called algebraic multigrid methods. Now as far as the algorithm is concerned, the basic algorithm or the format of the algorithm is same for both GMG, that is your geometric multigrid, and algebraic multigrid. In addition, we have got considerable flexibility in terms of the tweaking of these prolongation and restriction operators and the cycle of intergrid transfer sequences. That is, how do we use our restriction, in what sequence we use our restriction operators, in what sequence we prolong or interpolate our corrections from a coarser grid to finer grid. There are various strategies available. A few typical examples are V or W cycle. This symbol V or W, that stands for the way the restrictions and prolongations are employed. In fact, let us have a geometric look at our V cycle and why we use the symbol V here. So suppose the top level this is our what we call finest grid. We will assume an initial guess, compute our residual, next restrict that residual, go to the next grid level, this is a coarser or coarse grid, let us call it as 1. We want to stop here, further use a restriction operator, second use, and then obtain the residual on 8 coarse grid, which is even coarser than the coarse grid 1, let us call it coarse grid 2, and so on. We can have many sequence of such levels. So, this is coarse grid 3. So, suppose we have selected that okay, we are going to go for only 3 set of grids. So, use the restriction operator once, twice and thrice. So, at each level we have used restriction operator. At the coarsest grid level, then solve for the correction vector or correction term, and then once we have solved, we would basically solve a linear system which would be much smaller in size compared to our finest grid. So, we can use maybe a direct linear solver or a very accurate or converged Krylov subspace solution, or a solution obtained using any Krylov subspace solver which has converged sufficiently, and then this correction term would now be prolonged or what we call interpolated. So, prolong our solution to next grid, to next finer grid, to next finer grid. Ultimately, we would reach the finest grid level whenever where our solution is sought. So, if we proceed in this way, that is what is referred to as V cycle. Okay. We can also have W cycle, can be understood in the same way that we have got a sequence of grids. You go once, apply this restrictions and obtain a solution here, then prolong it, use the prolongation operators to get a correction term here. But instead of proceeding all the way to the top of the hierarchy, we might proceed only to the intermediate one level, and further we would obtain certain residual here. We would repeat the process, we will go back to the coarser and coarser grid levels, solve for the correction vector once again, and then do the final set of prolongations to reach to our finest grid level. So, this is the finest grid level. So, where this process has been done, this resembles our W symbol, that is the reason why it is called as W cycle. So, either of these cycles can be used. In fact, V cycle looks a bit simpler and is the one which is used most widely. Now, as I mentioned earlier, this multigrid method can be used as a stand-alone solver. That is to say, it can be used to solve a problem by itself, or it can be used as a preconditioner for a Krylov subspace method, for instance of a conjugate gradient or GMRS. So, it can be used as a preconditioner for PCG or GMRS. There are certain advantages of using it as a preconditioner, and for details of these different algebraic multigrid and geometric multigrid methods, please see the books by Saad and Trottenberg et al. There are a few other multigrid books, but these two were very good, specifically the book by Saad that will give us a compendium of all types of iterative schemes, including multigrid method and their parallel extensions. Before we proceed further, let us have a look at a sample multigrid algorithm. Okay. So, now let us have a look at a typical V cycle multigrid. Okay, we would use our symbols, for instance your system matrix is A. To denote a certain grid level we are going to use the subscripts. So, A subscript j, this would represent the matrix obtained at jth grid level. Similarly, P superscript j, this is restriction operator from jth grid to j minus 1th grid, and this P superscript j, this would represent our prolongation operator from grid level j to j plus 1. And we would represent our smoothing process as, let us say we have got a vector w. So, w over bar, that over bar would represent the effect of the smoothing process at grid level j. So, this wj bar, say w bar j, this is the effect of the smoothing procedure, which could be our Jacobi iteration or Gauss-Seidel iteration, used starting with the initial guess wj for system aj and right hand side given by this. So, this is our smoothing procedure. Now, with this notation we will say that how do we obtain our multigrid solution. So, multigrid algorithm is a recursive algorithm. So, a solution which we would obtain, that is x m plus 1 j. Suppose we are using V cycle, so let us call it V CYC in short form for our algorithm, or m j x m subscript j. So, this is our V cycle algorithm. Now, what is the expanded form of V cycle algorithm? So, VCYC is a recursive process which will depend on our grid level j. So, recursively do the following steps. First, let us check the grid level. If we have reached the coarsest grid level, so if j is equal to 0, which represents the coarsest grid. So, in this case what we will do, we will use a direct solver to solve the system A0 x 0 is equal to R0. So, this is what we do at the bottom of the grid level. Else we have to do a set of operations. These operations are called, first one we will have to do what we call pre-smoothing. So, pre-smoothing simply means that we have got our solution vector xm at grid level j, obtained its a smoothed version by applying a set of, or say a few iterations of our smoothing procedure. So, smooth, let us use a superscript nu1 to denote that number of iterations of our Jacobi or Gauss Seidel iterations which you want to use on, starting with the initial guess xm subscript j or system matrix Aj and this residual vector Rm of j. Okay, this new one could be as small as 2 or 3, that we might just use 2 or 3 iterations of the Gauss Seidel or Jacobi iteration for pre-smoothing. Then the next step is what we call defect computation. As compute the residual with the smoothed value of xmj which we have computed earlier. So, let us call this Rm j, this is equal to Rm j bar is equal to Rm j minus A of j xm bar j, and then it has to be restricted to the coarser grid. So, restriction process, sorry, we will go to the coarser grid level Rmj minus 1, apply the restriction operator or j minus 1 to our vector Rm bar j, and then once we have got the residual vector on coarse grid, then find out coarse grid correction. This is xm j is the previous value of xmj plus our projection operator at grid level j multiplied by the result of V cycle operated on our Rm bar j minus 1 at grid level j minus 1 with a residual of 0. And next is what we call, once we have got this coarse grid correction, we have to apply what we call post smoothing. Post smoothing simply represents that after post smoothing we will get our new iterate for the next multigrid iteration. So, xm at grid level j smooth. Let us say suppose we use new 2 iterations of a Jacobi process. So, xm j aj rmj. So, that is it, and f. So, if you look carefully, here we have got a procedure which calls itself, this V cycle algorithm itself calls it in the middle V cycle. So, that is why it is a recursive process. So, for actual details of algorithm and its implementation, please have a look at the 2 books which I have referred earlier, Saad and Trottenberg. Now, let us have a quick look at its application as a preconditioner. We have, let us say we want to apply or we want to solve our problem on a very complicated grid. So, on which generating a sequence of nested grids would be very difficult. So, what we can do is we can use a Cartesian grid, but use the geometric multigrid or generate the set of nested grids only for the rectangular sub blocks. So, on each rectangular sub block we can easily generate the sequence of nested grids, obtain the multigrid correction on that as a preconditioner and use that in our Krylov subspace solver. So, what we basically do is we have got a residual Now to get the residual vector or at each node, which may not be the part of our actual domain here, like these outer nodes, there will simply set the residual value to be 0. So 0 extension of our residual vector Rk, let us say in our PCJ. So extend it by adding zeros to get this residual term for multigrid. Similarly, we will set the initial guess Z0 at Z0k 0, and then we can use n number of multigrid cycles, that n could be 1, 2 or 3, at the most 3, that is what we will need to generate a solution ZML by using V cycle multigrid. So V cycle multigrid will give us a solution of the problem, starting off with this is our right hand side vector, and ZML that will give us the correction term. And next all that we need to do is just choose those components of Z and L which fall into our complicated domain. And this is what we applied using a Cartesian grid for heat conduction problem on 64 cube grid, which translates to few 100,000 grid points. And this is a comparison of two, that is our Jacobi preconditioner, which takes around 120 iterations, and this is our multigrid preconditioner. The solution converges to the tolerance of 10 to the power minus 8 in 30 to 40 iterations. So this was a grid size of few 100,000s. Now let us take a very complicated problem, and the system size is very large, it is 7 millions. It is a similar problem, Poisson equation for pressure, which is similar to a heat conduction equation. So for this problem involving few million, now here I have used a logarithmic grid to indicate number of iterations. This Jacobi, we need many thousands of iterations with our Jacobi preconditioner. With multigrid preconditioner, the number of iterations is restricted to 30. Similarly, I have also tried it for few billions. The number of grid points are in few billions, and again what we have seen is with a multigrid preconditioner, the number of iterations required are of the order of 30 to 40. So that proves our multigrid method, or along with multigrid preconditioner, we have obtained what we can call an optimal method, which does not depend on the size of the system. Now references, the book by Press gives us numerical recipe book, gives some algorithms related to the Krylov subspace solvers and their corresponding codes in C, C++, Fortran 77 or Fortran 90 language. Sart's book, this is a very comprehensive book on iterative methods including multigrid systems, and the Stroutenberg's book, this is exclusive to multigrid method, it discusses both geometric and algebraic multigrid algorithms for different partial differential equations. There are some web resources which you can consult, you can get free programs on them and reading material. Netlib.org, it contains the collection of different routines or algorithms based on the Krylov subspace methods. And this mgnet.org, this particular website is dedicated to the material related to multigrid methods, both geometric and algebraic multigrid. So I would strongly advise you to have a look at this mgnet.org website to have a look at the further details about the algorithms and programs related to multigrid methods.